I mentioned yesterday, we are very fortunate to have Dr. Tony Enright today with us, and he's got a wealth of knowledge in fire engineering, especially fire safety, and we're going to hear a very interesting talk today from him. Thank you very much, Tony. Thanks.
Thanks for that introduction, and thanks very much for that Project Everest presentation too. That looks like a really worthwhile venture. So from things going good to things going badly, we're going to talk about combustible cladding. I don't know if you noticed, but it's been in the news quite a bit over the last wee while. First of all, I'm going to start off by a simple illustration here of one of the properties of fire. Fires are buoyant, right? They go up. Now, one of the problems with combustible cladding, so what's cladding? Cladding is what we put on the outside of buildings on the envelope. Typically, just think of it as the stuff that keeps the wind and the rain out. But often it's installed vertically and it's installed over multiple stories. I don't know if you played with matches as kids, but I did. But this is a demonstration of the problem of orientation. So fires are buoyant. 70% of the fire's energy goes up in the plume. It's called convection, convective heat transfer. So on the right-hand side there, we're seeing what happens when you put the fuel in the pathway of the plume. Whereas on the left-hand side there, for the same amount of fuel, the heat transfer is much slower. It's mostly by thermal radiation and a little bit of conduction. It's a lot less intense and it spreads a lot more slowly. So over the last decade or 15 years, there's been some really high-profile fires internationally involving combustible cladding. Most numerously in the UAE, there would have been a dozen or so fires in the United Arab Emirates. And most tragically in the UK, in the Grenfell Towers fire of June 2017, where 72 people were killed. We've had two cladding fires here in Melbourne already, the Lacrosse fire, which we'll talk about in a moment, and earlier this year, in fact just a month ago, there was a fire on Spencer Street that went up. Fortunately, there were no serious injuries or fatalities, but there was significant damage done to the building. Actually, something I'll say at this point as well is that from what I've seen that you've been studying so far, you've been studying fire resistance. This is a different family of fire problems. This is reaction to fire. So whereas your structure, your primary elements have to resist a fire, this is mostly about secondary elements like cladding items. And they don't have to resist fire, but they're not expected to contribute to it as well. So this is the Lacrosse apartments during and after the fire. Very early hours of the morning on the 24th of November in 2014, a French backpacker came home from work and had a cigarette on the balcony, and he put his cigarette out in what he was using for an ashtray was like a plastic Yoplait yogurt container, which is not a great idea. So that caught on fire as well. He went to bed. The timber table it was caught on fire, and by then the fire got big enough to start involving the cladding. In this case, it's aluminium composite cladding, and it raced up the building. I've just got to go. I've remembered I've got a prop. I've got to grab my prop. So I raced up the building. It started on the 8th floor and reached the 21st floor in under 10 minutes. It also dropped down, really heavy dropped down. As you can see in that photo, there's another little fire starting 2 floors below. So on the 6th floor, it reignited there, spread to the 7th, and then rejoined the main fire. Now this sent shockwaves through everybody, particularly the MFB who were attending. There was no way it should have spread that fast. And in fact, they report that flames were shooting 10 metres above the building as well, so it would have carried on going if the building had been taller in all likelihood. There were several investigations, and the culprit is this thing we call ACP, aluminium composite panels. It's often also referred to as ACM, aluminium composite material. And what it is it's a thin panel system. It's got 2 aluminium skins. They're about 0.5 millimetre thick, and a core, and the core might be 2, 3 or 4 millimetres thick. The aluminium has a polymer on it for corrosion protection, and on the face side, the polymer also has some colour additives. It's very, very thin, about 50 microns, and it gives it a very distinctive metallic colour that you'll see around the building. I've seen it on a couple of buildings on campus already on the way in. And the problem is the core. So on the left-hand side there, we can see a sample which has got a black core. That's polyethylene, okay? That's a plastic. It's a thermoplastic. Most of the buildings in Melbourne, built before 2010 and maybe even 2014, had 100% polyethylene in the core. There are and always have been better varietals, They're the ones in the middle and the side, and that's where there's a mixture of polyethylene and non-combustible filler, so brucite or gypsite, so aluminium trihydroxide or magnesium dihydroxide. So they help reduce the reaction to fire. So the one in the middle there is quite a common product on the market now, and it's got only 30% polyethylene and 70% filler, and the one on the right has an even better reaction to fire. It's only got 7% polyethylene in it. There's still a little bit of polyethylene because it's a binder that keeps it together. Otherwise the core would be like brittle, like chalk, it would be brittle and break. So looking at the fire hazard from a macro point of view, this was an illustration from The Age, which I like, and they've given me permission to use. On the left there we can see our aluminium composite panel, 2 aluminium skins and a polyethylene core. Aluminium is a really, really good conductor, and because the sheet is so thin, the heat from a fire nearby transfers very quickly through the aluminium skin, only 0.5 millimetre thick, to the core. The polyethylene, on the other hand, is a very poor conductor. It's a very good insulator. So the surface heats up really, really quickly, and it causes it to melt. So like I said before, polyethylene is a thermoplastic, so it doesn't just burn like timber does, it melts first. And it melts at a relatively low temperature, 110 degrees Celsius. And that can cause the aluminium skin to delaminate. So the aluminium skin, aluminium alloy, is non-combustible, but once the fire gets at the polyethylene, then it combusts vigorously. Some of these materials, so on the lacrosse it was delaminated. On some of the better built buildings there are mechanical fixings, so they're in frames, and the steel frames can hold them in place. But aluminium has quite a low melting point as well, so even though if you fully encapsulate the edges, a building fire can get to about 800 or 900 degrees Celsius. You can get a fire in a laboratory, a flame temperature much higher than that, because real fires, building fires, are quite inefficient. So a diffusion fire will get up to about 800 degrees Celsius, but the melting temperature of aluminium is 660, so it melts and exposes the core as well. So even though it can be mechanically fixed, that's better, but it doesn't prevent the fire hazard completely. It's the first of the nerd slides. Right, so now your university students, this presentation was originally for the general population, so this will be a breeze. So this is the ethylene molecule. It's a monomer. When you get many of these put together, you get a polymer. So poly means many. Many ethylenes is polyethylene. 2 carbon atoms with each has a hydrogen atom attached to it. And then this is like a link in a chain, and the chain can go on for a couple of 100,000 links if you like. It can go on for a very long time. So as all atoms, so atoms everywhere, in your body, in your smartphone, in your seat, they're all vibrating at temperature. At any temperature above absolute zero, the atoms are moving. As they heat up, they move a bit faster, they get excited, and the vibrations start getting a bit more vigorous. At a certain temperature of thermal degradation, it'll get hot enough so that those bonds break. So for most organic solids, it's about 377 degrees. It's about 380 degrees, the high 300s. What happens is it heats up, the atoms are vibrating, and then the bonds break. So don't worry too much about this slide, it's a bit crowded. So we have our ethylene molecule there. In the presence of air, it oxidises. Combustion is basically an oxidisation reaction. So the oxygen goes, you beauty, and it attaches itself to the carbons and the hydrogens. And it forms CO2, carbon dioxide, and H2O, water vapour. So yeah, fire creates water. This is a stoichiometric equation, which means it's complete combustion. In reality, there's incomplete construction. Other products will be formed depending on what's in the air. You know, we have argon, we have potassium. But this is an idealisation of what goes on, and predominantly it will. The big problem here is that polyethylene and a lot of polymers, they take a lot of energy to make. The heat of formation is very, very high, whereas the heat of formation of carbon dioxide and H2O is a lot lower. So there's a lot of excess energy, and that energy is given off in the reaction, so it's an exothermic reaction. So just how much energy? Now we're going to test the volume.
So how combustible is this stuff?
A kilogram of polyethylene will release the same amount of energy as a kilogram of petrol.
I mean, it gets worse than that because polyethylene is denser than petrol too. So that's about a kilogram of polyethylene is like about 1.5 litres of petrol.
And so how many kilograms of polyethylene might there be on the side of a building?
If you look at a 1 metre by 1 metre square section, that will have about 3 kilograms, be equivalent to about 5 litres of petrol.
Right, so I have given this presentation wearing that same shirt before, but only once. Okay, this is the most important equation in fire engineering. And this, the property I was talking about just before, heat of combustion, is the one I've circled there. So this equation says that the heat release rate of a fire is the product of the mass loss rate times the heat of combustion. So what that means in reality is the power of fire, and by the way, fires, it's all about energy, okay? Things like temperature, we often talk about temperature, that's just a product of energy. It's all about energy. So the power of a fire is the burning rate, or the mass loss rate. So as solids burn, typically they pyrolyse, which means that they're getting lighter and lighter, so they're losing mass. So the heat of release rate is the product of the mass loss rate times the heat of combustion. So the heat of combustion is a good proxy for the fire hazard. The higher the heat of combustion, the more the fire hazard. What does a megawatt look like? Well, this is 2 megawatts. So in my PhD, a long time ago, I got to burn a whole lot of sofas and armchairs. So if you imagine that this was a single-seat armchair instead of a 2-seat sofa, then that would be what a megawatt looks like. So here we're extracting the gas away, the energy away, otherwise this room would flash over because this is a pretty hot fire for an enclosure. Also, just out of curiosity, the sofa's sitting on a scale, so as well as measuring the gases and analysing the gases, we're measuring the mass loss rate. So this is a little bit of a league table in terms of common materials and their heat of combustion. Again, heat of combustion being a really good proxy for fire hazard. So inert substances or building products like stone, glass and metal, they're non-combustible, so they have a heat of combustion of 0 or close to 0. A really good benchmark is wood, timber. So I mentioned before, you're going to move on to timber engineering. Structural timber is good, structural timber is thick, but timber on the outside of a multi-storeyed building is a bad idea. We've known that for hundreds of years, from the Great Fire of London, and even probably before that. For some reason, timber on the outside of buildings is getting popular again. I don't think it's a great idea, but the heat of combustion of timber is 16 megajoules per kilogram. So we can see polyethylene and its friend polystyrene are 2.5 times that. They're really, we've got a lot of embedded energy, equivalent to that of petrol. And it shouldn't come as a surprise because polyethylene and polystyrene are petrochemical products. They're made from crude oil. They're made from natural gas. That's where they get the feedstock for the carbons and the hydrogens. And we're wrapping our buildings in them, and we have been for a couple of decades. You notice I started talking about polystyrene. It's because the Victorian Cladding Task Force found that there's a proliferation of polystyrene on buildings as well. So we talk about EPS, expanded polystyrene. So these are mainly on the mid and low-rise buildings, so the 3 to 5 stories rather than the high-rise where you typically see ACP. You can see ACP everywhere. And this is because over the last 20 years or so, there's been a real drive for energy efficiency, and there's a big drive to insulate buildings to keep energy inside. And it's had this sort of unforeseen circumstance of people going, oh look, polystyrene, that's really light, it's a really good insulator, we'll put that on our buildings. They render it with an acrylic render, so you can see on the right-hand side there, it's actually quite hard to identify unless you go up and poke it with a needle or tap it or something like that. So a lot of the buildings look like they might have concrete, and in fact they've just got polystyrene on them. Polystyrene is a lot less dense than polyethylene, but the amount that we use it is a lot thicker, so it kind of balances out. So whereas the polyethylene might be 3 millimetres thick, polystyrene might be 100, and it's 1/30 of density, so it's about the same amount of energy. Unfortunately, in the case of EPS too, the acrylic render is really, really weak. It's really, really brittle, and it can break off. I'm not going to go through the stoichiometric equation again, but just to show you the second nerd slide. This is the ethylene molecule, very similar in structure with the 2 carbons and the hydrogens attached to it. And then there's this hexagon, which is called a benzene ring. So what it is it's got a carbon at each of the points on it, and it's got covalent bonds and single bonds to the carbon beside it, and then there's a free bond to hydrogen atoms. So it's no coincidence that in continental Europe and Italian and Greek and other languages, benzene is the word for petrol. So there's been a few clues here.
But polyethylene isn't the only dangerous product we're putting on our buildings. Now polystyrene is springing up too.
The product we're talking about is the styrene foam that's used in packaging and so on. If it burns, it'll melt. It'll melt like a marshmallow. There's a lot of it. There's an enormous amount of it now because it's a cheap means of construction. And when it's rendered with an acrylic render over it, it looks like concrete for all intentional purposes. Most people would think and believe that they've got a concrete building. Up on the building there...
Phil Dwyer is the president of the Builders Collective. He showed us this polystyrene-clad building in Melbourne. Earlier this year, a fire broke out in an air conditioner on a balcony.
It was fortunate that the fire happened at a time no one was around, no one was injured. The damage to the building was pretty contained by the sprinkler system. But to us, it was a really good example of other forms of cladding that are out there getting widely used in the industry.
In Melbourne, the fire brigade fears that in future, polystyrene could be even more of a risk than PE because it's used a lot on low-rise buildings, and they don't have to have sprinklers.
I think you've only got to go for a drive out in the suburbs and see the growth in the 3 to 8 storey building apartment sector to have some level of concern.
This 3-storey block has no sprinklers. In March, a discarded cigarette butt set alight polystyrene cladding on the balcony. A resident was badly burned trying to put out the fire. The burnt balcony was eventually repaired with new polystyrene.
There's a whole debate going on around whether it's compliant or not compliant. The issue we want to bring to everyone's attention is it burns.
This Melbourne building had to have fire screens added for protection. A building this high shouldn't strictly have polystyrene cladding, but it does. A fire engineer and a certifier both ticked off that it was being used safely.
This particular building was subject to a fire engineering analysis. A fire engineer has said that that's okay, and a certifier has checked that and approved it.
What do you think of it? Is it okay?
Absolutely not.
There's a view that deregulation and privatisation in the building industry have gone too far.
And if you were really eagle-eyed, you would have seen a heap of the ACP on that building as well. So just to wrap up in the last couple of minutes, so the Victorian Cladding Task Force recommended a statewide audit of all of the buildings for ACP and EPS, and so the Victorian Building Authority have been going through that as well. But there are a host of other combustible cladding products out there, maybe not so prevalent, and some are not quite so bad. These are sandwich panels. So you'll find these a lot in industrial buildings, although there's also one on actually more than one stadium here in Melbourne. The foam, the polymer in this is polyurethane, so rigid polyurethane. Also polyisocyanurate, PIR, I'm only going to say that once. PIR is not a thermoplastic, so it chars, so it behaves a bit better in fire, but it also has cyanide in it, so the gases are not particularly good. These sandwich panels on this particular building are steel encased. Now, steel has a much higher melting temperature than aluminium, way over 1,000. So, as long as they're jointed properly and encapsulated properly, they can isolate the hazard. My son and I, for many years, were members of the rugby team, supporters of the rugby team that play in this stadium. And every time there was a try, there'd be fireworks would go off and they'd land on the roof, and everybody would be watching the great screen for a replay, and I'd be looking up the roof to see if there's any glowing. Fortunately, they didn't get very many tries. Timber. Timber's not a good idea on a facade, okay? It's okay as beams and columns and cross-laminate timber. The building on the right is the City of Melbourne City Council offices. Worse than timber is timber on steroids. So this is timber composite, high pressure laminates. So these are made from waste products, so that's good, right? That's really good. They're about 80% of wood pulp, and then they're mixed in with resin, with glue, so with plastics. So they're about 20% more combustible than normal wood. So again, you know, they have their place, but not necessarily in a high-rise building. The dark grey stuff on this building is ACP. And this is a single stair building too. Yeah. And then there's other ones. So those photos are all from Melbourne, and this one was quite an infamous fire in the UK, which started off a parliamentary inquiry and started off a lot of thought into this. And the longer version of this presentation, it leads from this into the full-scale testing methods that were developed in the UK that we've adopted here in Australia as well. But yeah, the Scarnock Tower had weatherproofing problem, and it was this really bleak housing estate in the UK and in Scotland, and they decided to fix the corners and then to try and improve its aesthetics a little bit with fiberglass. But unfortunately, there was a fire in one of the apartments, and again, up it went. So we don't have time for questions today, but I'm going to hang around afterwards if anybody wants to come up if they have any questions or to see a sample. I didn't bring polystyrene. You can just see that in any package you buy. And by the way, I studied civil engineering as well. I mean, I'm hopeless at chemistry. I just had to remember a couple of formulas for this. Okay, thank you.